welcome to this particular lecture, and we will continue our discussion what we have been doing so far. So, we started doing the discretization for diffusion equation. So, we started with steady state diffusion equation, and whatever so far we have done in the front of numerics is that we have considered the orthogonal Cartesian grid system and derived our discretized equation for the diffusion equation, steady state diffusion equation. And in the process of doing so, we have looked at the individual term, how to calculate the fluxes, how to convert the governing equation to the final discretized equation, and then we looked at the implementation of boundary condition. And when we looked at the boundary condition implementation, that time we have come across 3 to 4 different kind of boundary conditions, like we have used the Dirichlet boundary condition, we have considered Neumann boundary condition, we have considered mixed boundary condition, we also considered symmetry boundary condition, and for all these respective cases we have looked at the formulation and the numerics part, like the discretized equation. So, in top of that, what we have also done is that when we considered the Cartesian system, we also took care of the non-homogeneity of the diffusivities, and to do the calculation for the non-homogeneity, we have come across the formulations or different methodology how to take care of the differences of the non-homogeneity. And then finally, what we have discussed or rather stopped in our last lecture is the calculation for the interface diffusivity. And interface diffusivity is an important parameter when you have the variation of the diffusivity coefficient along the space, then there is a non-homogeneity and you need to take care of that. And then we can calculate the interface diffusivity through different approach. One simple approach was to consider the arithmetic mean, and the second approach that we have considered the harmonic mean. So, these are the two approach that we have discussed, and both of them do have certain advantage and certain limitations of the applications. Like in top of the non-homogeneity, if there is a sharp gradient of the diffusivity coefficients across the cell interface, then the arithmetic mean may lead to a erroneous result. In that case, it is more preferred to use some kind of a harmonic mean. So, and that is where we have discussed these two things, and now once we have done all this, though we will move to the next level of discussion for the formulation for non-Cartesian orthogonal system. So, what we have done? Cartesian orthogonal. So, everything is restricted to the discretization of the diffusion equation. So, after we conclude or wrap up this diffusion equation, we will move to the next set of system is the convection diffusion. So, in this context, we have done the Cartesian orthogonal system, which is probably the simplest of the system, because here you have all the points which are orderly placed, the cells are orderly placed, and you can actually track the local indexing and global indexing in a simple fashion. And then from Cartesian orthogonal system, we will move to the non-Cartesian orthogonal system. So, that will be the next level to do that. In order to do that, in that case also we have to implement the boundary conditions, we need to take care of the diffusivity coefficients which is varying along the space. So, what just let us consider an example of a non-Cartesian system. This is the example of a non-Cartesian orthogonal grid system. So, here why we call it non-Cartesian? Because if you look at the grid pattern, the important thing to note here is that the discretized indexing which is shown here, these are all discretized indexing, and discretized indexing, they follow the similar pattern like the direction pattern that we have adopted for this particular class. So, this is what, or rather one can say that this is more a standard notation for any finite volume formulation. So, you consider a element C, and then ahead of that element is a standard notation of that element is east element, then the top of that or in the northern side is the north element, then behind that element is the west side element, and the underneath or the down of that element is the south element, and respective surfaces are identified like E, N, W, S, and all other S, F are surface vectors. So, these are all standard where F stands for small e, W, N and S. So, these are all standard notations that we are using, and but now this system is non-Cartesian. The reason is, if you look at it, this is our standard reference frame x and y system, and this has been offset by an angle theta. Now, if you, that is why it is a non-Cartesian system, but still this is orthogonal. The reason is that when you consider a particular element C, then all the surface vectors or the other elements like the surrounding elements, they are nicely ordered. Only difference is that the whole grid system has been shifted by an offset or by an angle theta. So, that is why it is a non-Cartesian system, but still it remains in the orthogonal mode, and so that allows to calculate the fluxes and all these things in a simpler fashion, that like what we have done for our orthogonal system, Cartesian orthogonal system. Now, to come back to the system, we you consider the one row of element. So, that if you look at it, essentially it is in a two dimensional system. Here it is a two dimensional Cartesian system or two dimensional orthogonal system. So, from here you come down to 1D system, and if you come down to 1D system, here you see the element C sitting here, and then east is only one element, west one element, these are the normal vectors, surface normal vectors, and then along this direction you have a normal vector and there will be a tangential component of the vector. The reason is all this stencil, it has been offset by our standard reference frame, and the other definition like the distance between the cell is delta x c, in the y direction delta y c, and also even non-Cartesian system the delta x c, if this is let us say delta x e, they are equal. So, delta x c must be equal to delta x. So, that uniformity is maintained. Only thing it is different from our previous Cartesian orthogonal system is that it has been tilted by an angle, and if we consider the this also, this would be also same. So, delta y c must be same with delta y south or delta y n, this is delta x west. So, that maintains the uniformity. And now, if you look at these distances, the distance between C and E, which is D C E. So, that is essentially the distance with a normal vector. So, that will get you that thing, and similarly you get the surface vector A C, you get the west opposite in side. So, you get both these things, and since it is one dimensional, we can get in a two dimensional similarly S n and S s. So, that will follow the standard procedure that we have adapted. So, now if you look at the discretized equation, so this should be essentially look similar to our Cartesian system, and we can derive that. So, how we can derive that? We will start with our equation. So, that is our standard equation, delta dot j equals to q. Now, this should be, once you write over the element c, this will turn out to be the surface integral, where f goes from NBC minus gamma delta phi f dot SF QC VC. Now, each phase we need to calculate the fluxes. So, once you try to calculate that JE dot AC, this would be minus gamma E delta phi dot N E AC. So, that will be essentially now minus gamma E del phi by del n at east phase with AC. Okay. Now, importantly here, this delta phi dot n at this east phase is nothing but del phi by del n at east phase. Now, this is the gradient of phi at phase E along the n direction. Why we say it is a n direction? If you look at this, the picture here, this is the n direction, that means the normal direction, and this is the tangential direction. So, normal and tangential directions are estimated. So, again what one can do, the simplest of the thing, that one can assume the linear variation in the profile of phi. So, if you assume the linear variation of the profile, then you can get the del phi by del n at surface E is phi E minus phi C divided by d C E. Okay. So, and why this is possible? Because this is possible for the reason the orthogonality is still there. Now, rest of the calculations for finally obtaining the discretized equation, so rest of the calculation are exactly similar as we have obtained for Cartesian system, Cartesian orthogonal system. So, this is the important point. So, rest of the derivation one can basically reproduce the as we have done for this case. Now, so what we have looked at this moment is that two important things. One is that we have got our discretization of the diffusion equation. So, essentially we are getting diffusion equation, the discretized one, using our numerical approximations. So, while doing that, we got it for Cartesian orthogonal system. So, you have got it in details. Then we got it for non-Cartesian orthogonal. Then we can go to non-orthogonal unstructured system. Now, when we move to non-orthogonal unstructured system, the things would be different. Why? Because in the Cartesian system, as long as they are orthogonal, they are actually easy to handle, because the elements or the cells, they are nicely ordered. As soon as we go to unstructured, that we have already come across or seen looking at the finite volume mesh, that they are not nicely ordered, they are rather randomly spaced. So, one has to keep track of lot of information starting from his elements, faces, nodes, and among them the connectivity through local indexing and global indexing. Okay. So, once we go to unstructured system, so these are non-orthogonal unstructured grid. First, we consider the non-orthogonality. So, we first consider the non-orthogonality, and to do that, the essential component would be the gradient calculation. So, let us consider this system for non-orthogonality. So, let us consider one particular element C. Okay. So, this is in non-orthogonal mesh. Okay. So, we have just considered one cell and then the neighboring cell F. Now, here they are not orthogonal. So, at the face, the surface vector SF, this is the surface vector which goes in the normal direction to the face. So, this is my face and this n is perpendicular to that F, and along the face this is the tangential direction. So, this is my normal direction, this is my tangential direction. So, at the face we got two different directions. So, one along this, and the connecting points between these two cell centers are connected through the line, that is the distance between these two cells DCF. Now, these lines which are also going through the point F at the face. So, initially we consider they are actually sitting on the line, or rather they are going to be sort of collinear. Then the normal vector is offset by a angle theta from this line. So, as it clearly shown, this is going by a angle theta, and now, so writing the gradient in this case as a function of this information. So, the gradient still would be a function of phi c, phi f and some other component, because due to the not orthogonality. So, now one has to write the exact expression for these connecting centers and the for element C. So, orthogonal grid, what we have obtained, if you just recall from the orthogonal grid what we have got. So, if it is the gradient in the normal direction, so orthogonal grid, the gradient in the direction normal to the face. So, what we have got, del phi dot n at face equals to del phi by del n at f, which is phi f minus phi c divided by sort of r f minus r c, which is one can write phi f minus phi c divided by d c f. So, essentially this is the distance vector between these two cell centers. So, here why we can write that? We can write here because C f and n is the unit normal vector, which is the n is, one can say that n is unit normal vector, okay, to f, the face. So, Cf and n are aligned, okay. So, that is why we can write these things, and connecting the points C and F we can obtain these things. Now, if E, which represents the unit vector along the direction defined by the line connecting C and F. So, E actually defines the normal vector or unit vector along the line C and F, which are joined along that. So, E actually represents the unit vector. So, once we do that, we can actually define the E. E would be Rf minus Rc, that is the difference between the radius vector, minus Rc, which is d Cf divided by small d Cf. Okay. So, that is what it is. So, essentially this is the mod of that. Now, you can find out the gradient along the direction. So, the gradient along E. So, this would be del phi dot E at face is del phi by del E at face, which is phi f minus phi c divided by R f minus R c, which also one can write that phi f minus phi c divided by small d c f. So, that is the vector. Now, if we linearize the flux, so linearize the flux in this particular system, in this non-orthogonal system, then the surface vector which was defined here, the surface vector SF. Now, SF will have two component. So, surface vector will be decomposed in two component, one is the EF plus TF. So, these are the two component that one needs to essentially decompose these surface vectors, and then what happens that I can write down the total surface vector in that fashion, where one can think that EF would be in the direction of CF, and that means they are connecting these 2 points. So, if you look at this SF, one component will go along this, which will be SF, some sort of a cos theta component, then other one will go along the tangential component, which will be the sin theta component. So, there are 2 components. So, now if I write down my diffusion flux, so there will be del phi F dot EF, that component, plus, because SF is the sum of these 2 component. So, it would be del phi F dot EF plus del phi F dot TF. Okay. So, if you look at it, this is along the direction of the CF. So, this part or this guy is nothing but my some sort of an. So, now I have connected these 2 points C and F, and the component which is going, the surface vector has 2 components, one going along this direction, another is going along tangential direction. So, this one, the one which will go along this direction E, they will be similar to our orthogonal contribution. One can think about in that fashion, because this is my cell which was connected C, F, they are connected from here, this is goes my SF, this goes my EF, this goes my TF. So, that is how the components are decomposed. So, this one can think about along this line, which is the line connecting between center C and center F, this will be looking like a orthogonal contribution. Now, what about this term? This term is another term which will look like an our non-orthogonal contribution. So, this is the first term will look like an our orthogonal contribution, which actually the component of the surface vector goes along this unit vector of E, other one goes along this direction, which is the non-orthogonal contribution. Now, if you compare to our orthogonal system, this is where the non-orthogonal system starts deviating from that. You do not have any contribution from the non-orthogonal system. So, one can write or expand this term in a slightly more detail. EF, this would be del phi by del E F plus del phi F dot TF. So, this one can write EF phi F minus phi C by dCF plus del phi F dot TF. Okay. So, this component actually involves the information of these 2 cell center C and F, and this is exactly looking like our contribution which we do get in our orthogonal system, but this extra term which was not present, sometimes this is also referred called the cross diffusion term. In some textbook they call it an orthogonal contribution, some textbooks call it a cross diffusion term or cross diffusion contribution. So, this is where the difference starts appearing between an orthogonal system and an non-orthogonal system. When you have a purely orthogonal system, you just get this contribution, and when you have a non-orthogonal system, you get this contribution and plus this contribution. So, this is the difference. Now, one can think about in another way, the orthogonal system is a special case of non-orthogonal system. Why? Because if the non-orthogonal system, this contribution goes off, then it turns out to be an orthogonal system. That means essentially one can derive and discretize equation for a non-orthogonal system, and then can be used for both non-orthogonal system and an orthogonal system by assigning the term like the non-orthogonal contribution term to be 0. So, that is the one of the beauty of finite volume method, that things can be more generic in nature, and once we go along with the complexity, you can see that the higher level things can be always simplified to the lower level one. Though we are starting from the orthogonal system, then moving to a non-orthogonal system, the non-orthogonal system can be boils down to orthogonal for a special case, as it is here. Okay. Now, the point comes, how do you decompose this SF? When you decompose this SF, or if you put back the SF, you get this particular equation. So, we will stop here and thank you.